So what is a power series? So you can see what is the difference between this thing that we're calling a power series versus the other types of series that we're. Well, notice that this one actually has a variable in it, right? It's got that x in it. The ones that we've been dealing with now, there were no variables. It was just numbers, right? A bunch of numbers added together. Now, what are we adding together? We're adding variables, you see? And that x, it's just a variable just like you would have in any other function, like sine x or cosine x or whatever, right? Okay, so in fact, if you look at this thing, what really is a power series? What does that kind of look like? I mean, if I were to not have these on the end here, if I just chop that off and I just stopped it right there at x to the n, what does that look like? Doesn't that just look like a nth degree polynomial? In fact, that's what it is, right? It's just an nth degree polynomial. So what is a power series then? Power series is a strange kind of new thing, but it's just an extension of something that we've already seen multiple times throughout the years of math that we've been doing. It's a polynomial, right? Except in this case, it's a strange polynomial because those just keep going. It's not an nth degree polynomial. It's an infinite degree polynomial. That's what a power series is. Infinite degree polynomial. It turns out you can do some pretty weird things with infinite degree polynomials. In fact, you can, with these things, make them so that they are exactly equal to any other function that we're familiar with. For example, I can find an infinite degree polynomial that will be exactly equal to, say, the sine function, or the cosine function, or e to the x, or any function that you can think of. There's an infinite degree polynomial that is exactly the same as that function. This one here is centered, I'll put that in quotes since we're seeing it for the first time, at x equals 0. The center of a power series is the number that will make all the terms of the series 0. Okay? Notice that if you plug in 0 for all these x's, right, if those are all 0, then the whole thing is 0, right? Except for the first term, in fact, except for the first term. And so basically it's the center of a power series is the term that if you plug it in, all you're going to be left with is the constant term. Everything else will be 0, okay? And so you can see that if I have a power series that looks like this, for example, where I put an x minus a on there, what number will make this thing 0 now? All the terms except the first one. Well, you can see maybe if I plug in the number a for x, right? If x equals a, what happens? Well, then I get a minus a, right? 0. And so all that's going to be left there is just the first term. So the center of this power series is at a, okay? This is centered at a. Everybody clear what I'm saying when I mean the center of a power series? It's the number that you plug in, whatever you plug in right there for x, that makes that 0. That's the center. All right, now what are power series? I mean, we've already said they're infinite degree polynomials, but really, I guess more generally, what these things are, they're functions. Power series are a special type of function. Okay? Let me give you an example of what I mean by that. So here's an example. What if I give you this as a power series? Okay, that is a power series. That qualifies because the CNs in this case this is the CN right here, right? 1 over n squared. So why is it a variable? Well, it's a variable. In fact, I can even call it a function. I call it f of x equals, right? Just like we do with normal function notation. Well, that means that I can ask you, for example, like what is f of 1? Right? What's f of 1? Well, how do I find f of 1? I would just plug in the 1 for the x. So I get this. If I plug in 1 for x, I'm just going to get this, right? And you see that that is itself a series, right? That's the series that we've been seeing up till now in these other sections. Now, that series, it turns out it does have a sum, right? It has a sum. Pretty hard to find it. In fact, I think there was an example of this, like pi squared over 6 or something like that. But you see there is an output, right? There is an output associated with this particular power series. When I plug in the number 1, depending on what numbers I plug in here for x, I may or may not get an output, right? Suppose I plug in a number there for x that I don't get an output for some reason, right? There's no output at all. maybe you get a series that diverges when you do that, right? If the series diverges when you plug that number in, that just means that the number you plugged in is not part of the domain of the function. So what we're trying to do here when we're trying to find out whether the numbers that we plug in are going to produce a series that converges or not, it's kind of like we're trying to find the domain of the power series is really what it is, or the domain of the function. And so it turns out for power series, one of three things can happen. It converges only at the center. And remember what I'm saying, does it converge for what values, right? That means these are the x's that I'm talking about that you can plug in here, right? Like I said, this is f of x, and you can plug in numbers for x. Now the question then becomes, well, which numbers is the resulting series like that after you actually do plug a number in? For which values is that actually going to converge, and for which values isn't it going to converge? Okay, and so that's what we're talking about here. When is it going to converge, and what can possibly happen here? Well, it turns out these are the only three possibilities. It's either only going to converge at its center, and you can see that any power series must converge at its center, right? You come back up here and say, what happens when you plug the center in, right? You get zeros there, right? Of course that has to converge. If you add a whole bunch of zeros together, you're just going to get zero, right? And so it's going to converge to zero, or whatever that, that constant term at the beginning is. Or potentially, what else could it? Or actually, let's look at the third one first. It converges everywhere. That's a nice one. If it converges everywhere, that means it doesn't matter. You can plug in whatever x you want, and you know that it's going to converge. In fact, if you see a series like that, that just means its domain is all real numbers. Okay. If you see a power series like that first one, its domain is just a single number, just the one number that you can plug in. What about the third, the second one that I haven't written here? What's the other option here? It says that one's maybe a little bit harder to understand, but it says there is some real number for which it will converge that far away from the center. What I'm going to do for that second one is just kind of draw it. The other possibility is this. You have the center, right? Here's the center of the power series. What they mean by that is it could potentially converge some distance away from the center. But if it does this, the nice thing is that we know whatever it does, it's going to do that the same distance to the left as it does to the right, okay? Which is kind of nice. And this R value here is called the radius of convergence. So basically what that does, if you find that you have a particular radius of convergence, then what that means is that the power series is going to converge for all of these values. Basically from here to here, it's going to converge if you plug in any of those x values. And then it's going to diverge outside of that window there. Okay, so basically, again, what we're trying to really do here is determine the domain of these power series, which I said they are just a special fancy kind of function. So all of this stuff that we're going to be doing here is basically devoted to finding the domain of a power series. What is the domain of a power series? And remember, a power series is just a function, so we're really just finding the domain of this interesting new type of function that we're seeing here. So let's see how we do this. How do we determine this radius of convergence for a power series? And so let's look at that first example there. What is the radius of convergence for this power series? And also keeping in mind there's actually two types of questions you might be asked here. Find the radius of convergence, and the other one is to find the interval of convergence. We'll see what the difference is here. This one's only asking for the radius, which is a little bit easier. Okay, so the way that we do this, the way that we determine the radius of convergence is this is what I was saying, the ratio test is the most used because we always start questions like this with the ratio test. Okay, there's no other test that we use here. It's always the ratio test. And then when we're trying to find the interval of convergence, we may use another test to determine what happens at endpoints. Anyway, so the ratio test says, again, you take the AN term. In this case, the absolute values are essential. We have to have them here, and we'll see why in a second. And I'm going to go ahead and include the -1 terms, even though we know what's going to happen with those right after the first step. And be careful, again, on this replacing n by n plus 1. Again, the only thing you need to replace with n plus 1 is just the n. Anything else that's being done to it has to still be done to the n plus 1. And I'm telling you this because a common mistake here is to just write that as 2n plus 1, where you don't put the parentheses around the n plus 1. And you can see the problem with that. If you don't put the parentheses, you're definitely not going to get the right exponent there, right? If the parentheses are there correctly, as they should be, you see that that gets distributed and it becomes 2n plus 2. So don't forget to put the n plus 1 in parentheses, especially if it's being multiplied by something else. And same here in the denominator, right? 2n plus 1, and then all of that has the factorial applied to it. Okay, and then again, we flip over the nth term, basically just copy the nth term and flip it over. Okay, so this works pretty much exactly as the ratio test did before, except now we have these x's in here as well. So we have to think about what's going to happen with that. And like I was just saying, we know we have absolute value bars around this thing. So since we do, any negative terms are immediately going to just cancel or just go away. We cross them off immediately because of the absolute value bars. And then what's left? So let's simplify this. We have x minus 1 to the power of 2n plus 2. We've got 2n factorial here. In the denominator, we've got 2n plus 2 factorial. And then we've got this x minus 1 to the power of 2n. All right, so let's think about how we can rewrite these things to make some stuff cancel out. Oh, I'm sorry. I still need to put the absolute value bars in. We'll see why in just a second here. Okay, so let's write that x to the 2n plus 2. Remember that with the properties of exponents, you can write this as x minus 1 to the 2n times x minus 1 squared. Right, that's just property of exponents. That 2n factorial is still there. This 2n plus 2 factorial, this is something we need to cancel. So let's write this as 2n plus 2, 2n plus 1, and then 2n factorial. Just so we can cancel that 2n factorial in the numerator. And then I'm going to still put the absolute value bars. Okay, now writing it like this, you can see a bunch of stuff's going to cancel, right? All of that. Something that we need to sort of be aware of here. This is the limit as n goes to infinity, right? Now, this term right here, notice, doesn't have an n in it at all. There's no n anymore, right? We canceled all the occurrences of n there. And so that means, for the purposes of this limit, we can treat that as if it's a constant because it does not depend on n, right? If it doesn't depend on n, it can be brought outside of the limit. And so I'm going to do that now. And just by the way, if this were not squared, if this were just an x minus 1, this is why the absolute value bars are important. Because if that were not squared, then it has the potential for that to be negative, right? I could pick an x value for that thing to be negative. And so those absolute value bars, they need to remain around that x minus 1, okay? In fact, I'll put them, even though it doesn't really matter here because it is being squared, but this is what you would do on that step. You would take out that x minus 1, and the absolute value bars have to stay around it. And again, in this particular case, they're not necessary just yet because of the being squared, but still, it doesn't matter if you put them when they don't need to be there. All right, then what's left? After what does it still depend on n here? Well, the only thing that we have left in the numerator, now we've taken that x minus 1 squared out, is just a 1, and then we have in the denominator 4n squared plus 6n plus 2. Well, we can see what happens there, right? As n goes to infinity, well, all the n's are in the denominator, so we know this limit has to be 0. So if the limit is 0, what that's telling us is that it doesn't even matter what x is. Like, I can put in any value for x here, right? I can plug in whatever number I want for x. Whatever I plug in, it's not going to matter as far as this limit is concerned, because we did the ratio test and we got down to this point right here. No matter what I plug in for x, I always get 0. Well, for the purposes of the ratio test, what conclusion do we have to make? Well, 0 is less than 1, right? And what does the ratio test say? It says as long as you get a number less than 1 for the limit, then it converges, right? And so since this is 0 no matter what x is, this means this converges for all values of x. If it converges for all x, that means the radius of convergence, in other words, how far away from the center is it going to converge? Well, again, if it converges for all x, the center is at 1 in this case, that means it's going to converge infinitely far away from the center, right? No matter what x is, it still converges. So the radius of convergence is actually infinite in this case. We have an infinite radius of convergence. So that's, again, if you think about, like what we're actually trying to do here, what we're trying to determine as far as these power series are concerned, if you have an infinite radius of convergence, that is the best situation as far as being able to use the power series for something, who knows what, right? But if you know that you have an infinite radius of convergence, you can plug in whatever you want, and this thing is going to produce a reasonable, usable output value. Okay, and in fact, another way to think of, I think I mentioned this last time a little bit, another way to think of this interval and radius of convergence is to think about it as the domain of the power series. Like, which values of x can I plug in here and expect to get this sum to actually be a number, right? To have that be a number rather than to be infinity or just undefined. Okay. So when we see that we have an infinite radius of convergence, that's another way of just saying the domain for this power series is all real numbers. Okay. And in fact, they don't ask for it here, but you could also say the interval of convergence, that's like the entire interval, is all real numbers, minus infinity to infinity. And again, that could also be viewed as the domain of the power series. All right, let's try another one. So number 2, radius, just the radius of convergence here. So this one, the test will be pretty simple because it's not a very complicated power series. The terms in here are pretty easy to deal with. So anyway, ratio test still, that's the first thing you do. You take the limit as n goes to infinity, absolute value, replace the n with n plus 1. So n plus 1 there, n plus 1 there. Multiply by the reciprocal of the nth term. Again, the absolute value bars are important here. Now, in this case, I'll write the step, but you don't necessarily have to write this step every time. You can probably just think about this as thinking about properties of exponents. X to the n plus 1, x to the n. Well, how do you deal with that when you have some number raised to a power divided by the same number raised to a different power? You subtract the exponents, right? X to the n plus 1 minus x to the n, that just leaves you with x. So if you want to think of it like that, you certainly can, or you can do that, other property of exponent thing where you write it as x to the n times x, however you prefer. And then we have that n to the third, I have n plus 1 to the third. We have x to the n here. So now we can see either way that that's going to cancel. We're just left with an x there. Now this is where the absolute value bars are important, because this x here does have the absolute value bars around it, right? Well, that x could be anything because that's a variable, right? Could be any number, including a negative number. And so we want to still indicate that we can't have negative numbers here. So those absolute value bars have to stay around that x. And the x doesn't have any n's with it, so that means we can pull it out of the limit. So we'll pull it out, including the absolute value bars around it, and then what are we left with? What terms do have n that are left here? N to the third, and n plus 1 to the third. Okay, now that limit is just 1, because if we were to expand that denominator, we would find that it's a third-degree polynomial. Leading coefficient is 1, and the leading coefficient of the numerator term also is 1, and it's also cubic, so we're just left with 1 for the limit, but we still have that absolute value of x there. Okay. All right, now this is where things are a little bit different as far as how do we determine what to do with this, right? How do we determine where this actually converges? Well, this is the limit that we got. That's the limit we got after we did the ratio test, right? Now we have to think, okay, well, what does the ratio test require? For convergence, what does that limit have to be? Well, remember what the conditions for convergence are on the ratio test. It has to be less than 1. And the limit that we got is this, absolute value x. And so that quantity is what we would need to be less than 1 for convergence to happen, okay? And in fact, this right here is now the radius of convergence, okay? Because we know it's going to converge a distance of 1 away from the center, which is 0. I'm going to start abbreviating it as ROC, radius of convergence. And again, if you think about what that actually means, absolute value x less than 1, you can write that as a triple inequality, right? Anytime you have the absolute value of anything less than 1, thinking way back to your intermediate algebra class, you can always write that as an as a compound inequality, where the thing that this quantity here, x, is greater than the negative of that, but less than the positive of that. That's what the absolute value being less than a number actually means. So that's the compound inequality that you get from that, okay? And again, if you think about, what I said about the center of a power series last time, the center is the value that makes the whole thing 0. Well, if I plug in x equals 0 there, then that makes the whole thing 0, right? And so that is the center. 0 is the center. And so thinking about the radius of convergence, if you draw this on a number line, for example, and you put the center 0 right in the middle here, what we know is going to happen is that it's going to converge around this center, starting at -1 and ending at 1. Okay? So if I plug in any x value between -1 and 1 into the x up here, and again, think about what that means. So what would I have to do? I'd have to think about plugging in 1/2 there or something like that. If I plug in 1/2 for x, then we get 1/2 to the n over n to the third. I know that that's going to converge because 1/2 is less than 1. 1/2 is on this interval that I just drew here. Okay, does everybody kind of follow what we're thinking about here? Again, the other way you could think of this is the domain of this particular power series. Any number that I plug in between -1 and 1, I know that this power series up here is going to turn into, once I plug a number, into just an infinite series, and I know that that series is going to converge to some number, right? And that number that it converges to then would be part of the range of the power series, right? It would be like the output value of the function. And if I plug in a different x on that interval, then I'm going to get a different output, right? It'll converge to a different number. But you can even actually graph these things. This is actually something just to get a better idea of what is going on with these things. Let me actually just show you that you can actually graph a power series. So let me show you how you might go about doing that. This is a good problem, I think, to demonstrate that. I'm going to go ahead and share Desmos real quick so we can actually graph this power series and see what it looks like when you graph it. You recognize that it actually is a function. So I'm just going to try to enter this same one. And the way that you have to do this is you have to enter some finite value. You can't enter infinity on this. So yeah, there we go. So that's it. That's the graph of this power series. And so you can see, where does it converge? It converges between -1 and 1. Since I can't graph this to infinity, what I can do is just make that bigger. Like, what if I make this 50 instead of 10? So it looks a little bit different, right? It looks a little bit more sharply defined there, perhaps. And then I could put in maybe 100. You can see that it takes a little while for my computer to actually figure out what's happening. Because if you think about when I put 100 on there, what is that actually telling the computer to do? Well, remember that this is a summation, right? And so I could start at n equal 1. And if I start at n equals 1, what's the first term? It's 1 over n to the third, right? I'm sorry, it's x, yeah. It's x to the power of, or x to the first power over n to the third. And then when n is 2, or I guess 1 to the third, and then when n is 2, what do I get? Then I get x squared over 2 to the third, so x squared over 8. And then I'll have what, x to the third over 27, and then I'll have x to the fourth over 81. And it's going to keep doing that until I get to the 100th power on x. So by putting this 100 up here, what am I telling the computer to actually graph? I'm telling the computer to graph a 100th degree polynomial. X to the 100th times some coefficient plus x to the 99th times some coefficient, all the way down to that first power. So that's a 100th degree polynomial that I'm asking the calculator to graph, the computer to graph. If you tried to put a 100th degree polynomial in your TI-84, it wouldn't even do it. I mean, it would, but it would take probably days to figure out what the graph actually looks like. This computer is really fast, and you can see it even takes a little while to think about what the graph is supposed to look like. And think about what would happen if I put 1,000 on here, right? If I do put 1,000, it's going to sit there for quite a while. So my computer is now churning away, trying to think about what a 1,000th degree polynomial is going to look like when I graph it. Oh, and I guess I should probably attempt to show you what happens when you put in like an odd power. Let's see what happens when I put in the 99th power. Oh, it finally graphed that 100th degree. But you see the 100th degree one. Yeah, see, look, there's the 99th power. I don't know why they're both going up on the end there. Isn't the odd degree one supposed to go down? Yeah, there it goes. See, it's down on one end. That's an odd degree polynomial, 99th degree. So every odd degree polynomial acts like an odd degree polynomial, right? Like a cubic. Every even degree polynomial acts like an even degree polynomial, where it goes up on one side, up on the other side. So again, you can see the 1000 one really shows you that the interval of convergence is from -1 to 1, right? Where after the computer finally figures it out, look where it's that little corner right there. It seems to be a little bit farther away from 1. I'm not sure why it's quite doing that, but anyway, it's really close to 1. That's where it stops actually. Yeah, there we go. See that? That's really close to 1, right? So that we can only assume that the actual output value of this power series is accurate only on that little bit from -1 to 1. Everywhere else, it's like going off to infinity, or perhaps negative infinity if it's an odd degree polynomial. All right, so anyway, you can see power series are functions. They produce graphs just like any other function does. The graphs that power series can produce, really, you can make it produce almost anything, which is the nice thing about power series. All right, and so again, if you were to have a power series that converged for all values of x, you wouldn't see this behavior here where it sort of just rockets up to infinity on both sides like that. It would actually look like a function everywhere. Okay, so anyway, now we kind of maybe get a little bit of a better picture about what that radius of convergence is actually telling us. It's only going to actually produce a usable function exactly that distance away from the center. Now, example 3, this one, notice, is not asking for the radius, it's asking for the interval of convergence. The interval is the entire interval where it converges from the left endpoint, comma, up to the right endpoint. So that's like an interval where you have to put the bracket or the parentheses to indicate inclusion or exclusion. All right, so let's take a look at this one. It says that we want to find the interval of convergence, but in order to find the interval, we first have to find the radius. So we start out exactly the same way as we did before. So we find this limit according to the ratio test, replace all the n's with n plus 1. Again, being careful to put them in parentheses. Multiply that by the nth term flipped over. Okay, and then simplify this a bit. So let's write this as 4 times 4 to the n. Let's write this as x minus 2 to the n times x minus 2. And I'll just leave this as 5n. Okay, so let's see what happens there. Well, those 4 to the n's are going to cancel. The x minus 2 to the n's are going to cancel. The constant terms that we can take out the limit here, that 4, and again, this x minus 2 can be viewed as a constant since it doesn't have any, at least for the purposes of this limit, since it doesn't have any n's in it. But remember that when you take that out, the absolute value bars have to follow it, because that could potentially be negative, and the absolute value bars are making sure that it isn't. Oh, and I guess let's fix this a little bit. This 5n plus 5, we could factor a 5 out of that, right? And make it 5 times n plus 1, and then we can cancel that 5 and that 5. Leaving us with what's left over. So it seems that we still have an n up there in the numerator, and we still have an n plus 1 in the denominator, but that's it, right? Everything else we've either taken out or it's canceled. Okay, so now what is that limit? Well, n over n plus 1 as we go to infinity, that's just 1, and so our limit here is 4 times absolute value x minus 2. Okay, that is the limit. That is the quantity, according to the ratio test, for convergence to happen. That quantity that we just got has to be less than 1. So for convergence, this quantity here that we got for our limit has to be less than 1. Okay, so when you get to the point where you just have this term here, x by itself minus a number, when you get to the point where you just have that, in other words, we have to divide by that 4 there. So when you reach this point where you just have x minus a number, x minus a, less than something, right? Less than some number here, we'll call it r. Once you've reached this point, the thing that is on the right side here, that is the radius of convergence, okay? This is telling us that it's going to converge 1/4 away from the center. The center in this case being 2. Okay, remember the center is the number that makes the whole thing 0. And so in this case, coming back to the original function there, the number that makes that 0 is 2. And so 2 is the center of this power series. And so what this is telling us, once we reach this step here, the x minus the center is less than a number. That number is the radius of convergence. So if we were only asked for the radius of convergence, in fact, we'd be done with this problem. But now we're asked for the interval, so we have to keep going. And the next step is to say, okay, well, let's change that absolute value inequality to a compound inequality. Remember how you do that? You take the negative of the thing on the right, and you put the x minus 2 without absolute value in the middle of it, and then you put the positive of it on the right. Okay, so that's the compound inequality that you get from that absolute value inequality. Right now we need to solve this for x, solve this inequality. So what I'm going to do is add 2 to everything, right? So add 2 to everything. So 2 minus 1/4 is 7/4, right? And 2 plus 1/4 is 9/4. Okay, so this then is telling us, again, if you think about on the graph, what's happening here? What's happening? Well, the center of this thing is 2, so I would put like 2 right at the center here. 7/4 is a little bit less than 2, right? So 7/4 is over here. 7/4 is like 1 3/4, I guess, right? And 9/4 is like 2 1/4. What this is saying is that this power series, if I pick any number between here and here, any number between 7/4 and 9/4, and I plug it in to the original power series, plug it in for x, right? That's like a variable. Then the resulting series, and the resulting infinite series, just like all those ones we saw up until 11.6, we know it's going to converge, okay, by the ratio test, since we just did the ratio test on this thing. Okay, now, why does the interval take a little bit more effort here? Well, we're still not quite done, because if you think about it, what would actually happen if I put either of these numbers themselves in? Like if I wanted to know what happens when I plug in the number 7/4, or the number 9/4 for that matter, well, what's going to happen if I do that? Well, think about it. Say I come up here and I plug 7/4 in right there. 7/4 minus 2, that's negative 1/4, right? When I take the absolute value, I get 4, and then I multiply it by that other 4. What do I get? I get 1, right? So plugging in either of these endpoints produces the number 1 right there. But where is that? What is that thing that I just circled? That is the ending step of the ratio test, right? And so if I plug in either of those endpoints, my ending step on the ratio test is going to be that I get the number 1, okay? What happens when you get the number 1 as your last step on the ratio test? That is the one problem value for the ratio test. Inconclusive, exactly. And so what that means is that the ratio test is not telling me what is going to happen at those two endpoints, at 7/4 or at 9/4, because if I plug either of those endpoints in there, I'm going to get the number 1 for the result of the ratio test. Well, it's inconclusive. So what do I do with two endpoints? That's telling me that they could either be included or excluded. We don't know, because the ratio test isn't telling us. Well, unfortunately, what it means is that we have to use a different test for the endpoints. So the endpoints, unfortunately, are going to require a different test besides the ratio test. When I told you earlier that the ratio test is by far the most commonly used one, well, this is why, because the ratio test is the main one that we use for finding the interval of convergence. But it doesn't work at the endpoints. And so that's why, one of the main reasons why we have to have all those other tests that we talked about. The ratio test is going to fail. We know that. So we have to try another test. And so we have to check the endpoints separately with different tests, or possibly tests. We might have to use two different tests, one for each endpoint. Okay, so let's do that. Let's check the endpoints. Let's check x equals 7/4. So how do I check it? Well, I just have to go back to the power series that I started with, and I have to plug 7/4 in for x. Okay, so that's exactly what I'm going to do. 7/4 here, minus 2 to the n. And again, by doing this, I'm just producing a series just like the ones that we've been talking about up until this section, right? All the way up to 11.7. Okay, so let's see, 7/4 minus 2 is negative 1/4, right? So we got negative 1/4 here to the n over 5n. Now that negative 1/4, I can write that differently. Since it's to the n power, I can write it like this. I can write it as negative 1 times 1/4, right? And then I can apply that n power to both of them separately. Okay, now notice this 1/4 to the n could also be written as 1 over 4 to the n. So it's going to cancel with the 4 to the n there. And then that 1/5 can be brought out. It's a constant. And this is what we're left with then, negative 1 to the n over n. What kind of series is that? Since it has that negative 1 on there, it's got to be an alternating series, right? Okay, alternating series. So how do I test this one then? I have to use the alternating series test. Okay, so use alternating series test to check this thing for convergence. In fact, this one is a special alternating series, just in case you're interested. This is called the alternating harmonic series. If you do end up with the alternating harmonic series, you can just say that it is the alternating harmonic series, and we know what that one does. In fact, it converges. So you could actually skip this step and just say it's the alternating harmonic series, but I'm going to go ahead and do the tests anyway. What are the two parts of the alternating series test? Part one is that I have to show that 1 over n plus 1 is less than 1 over n. Well, that's an easy check there. And the other one, the other part of the alternating series test is that I have to show that the limit is 0 and the terms, the non-negative. Easy test, that just shows that this thing does converge at x equals 7/4. So this passed the alternating series test, converges at x equals 7/4. And it did that because it passed the alternating series test. Okay, what about the other endpoint? Let's see what happens there. And you don't really have to do as much writing as I'm doing here. I'm just trying to make sure that everything is clear about what we're doing. So the other endpoint is 9/4. And again, how do I check it? I take the series that I was given, the power series that I was given, and I plug in the number 9/4. So 9/4 minus 2. Well, what's 9/4 minus 2? 1/4, positive 1/4. So I get 4 to the n times 1/4 to the n. Okay, and I know, again, in this case, I don't have a negative, and that's just going to cancel. And here you can just take the 1/5 out again, and you're left with 1 over n. Now that is the actual harmonic series. I don't think I mentioned that before. It's just a p series with p equal to 1, and that's perfect explanation for why it's going to diverge. However, it's also a p series with p equal to 1 is also called the harmonic series, in case you're interested in that. Harmonic series because it does have to do with musical notes there. If you take an object that is 1 unit long, and then you apply every term of the harmonic series to it, like 1/2 would be the first term, right? So that, in other words, you take a rod, say that when you strike it, it makes a tone that's 1 unit long, and then you take one that makes a unit that's half that long, 1/2, and you strike them both at the same time, you get harmony. And the same thing would happen if you cut it to 1/3 of its original length, or 1/4 or 1/5 or 1/6. Any of those lengths, if you strike them all at the same time, it will produce a nice harmony. It's called the harmonic series for that reason. Anyway, the harmonic series is divergent. And again, here you can just say this is either the harmonic series, or you could just say it's a p series with p equal to 1. That's perfectly acceptable as well. And so no test involved other than just to say it's a p series, or that it's the harmonic series. Okay, so what have we just done? We have now tested both endpoints using other tests, or just noticing that it was a p series. So what is the interval of convergence? So the interval, and I'm going to abbreviate this as IOC, is what? Well, again, the only thing we really didn't know about it was what the endpoints were. We already had almost the entire interval, 7/4 to 9/4, right? So now we know that it converged at 7/4, but it diverged at 9/4. And so we include one and we exclude the other. Or if you want to write it in interval notation, you could do that too. You could say 7/4 excluding 9/4, including 7/4. So now we know exactly what it does on the entire interval. Now, of course, there's also the issue of like, well, what kind of convergence do you have going on at those endpoints, right? We don't really address that, but it is something that maybe needs to be thought about a little bit as well. Like at 7/4, if you notice, what did we actually end up with right there? We ended up with this thing here, right? Well, if you notice, that thing is actually only conditionally convergent. So it may be almost as bad as diverging since it's conditionally convergent at that endpoint. Anyway, it's not something that we really address, but something to maybe make a note of. But anyway, for now, let's go ahead and at least try to do these two problems. So notice that the first one is only asking for the radius, and the second one is asking for the interval of convergence. So, first one you don't have to do as much. Second one, you have to go on and check the endpoints as well. Okay, so let's just quickly kind of go through these. So that first problem, only asking for the radius of convergence. You can see that Michael's done the ratio test here. At the end of that, after all the simplification, we're just left with this. There's that right there. Yeah, I guess that other one we had squared didn't do this. Yeah, when it's squared like this, just be aware of what's going on here. Second power there is kind of important. When you're at this step right here and you multiply by the 4 and you get the 4 over there, you have to have it to this point where there's power on here either. It has to be just x minus the center to the first power. Once you reach that point, the thing on the right side here is the radius, as Michael notes here. And then another thing just to be aware of is that when you take the square root of x squared, right here, there's not absolute value bars on there because they don't need to be, because squaring something makes it positive anyway. But when you take the square root of x squared, like if I have x squared here and I take the square root of it, well, what is it really? It's not just x, right? Because if it's just x, then that would allow for x to be a negative number. In fact, it's probably better to write it like this. If I take the square root of x and then I square it, I can take a negative number and plug it in here, right? No problem. So in order to account for the fact that these numbers can, or we don't want them to be negative, right? We actually don't want them to be negative. You have to put the absolute value bars around it after you take the square root. So really the square root of x squared is not just x, it's the absolute value of x, okay? And I guess if you write it the other way, you can kind of see that as well. But anyway, the point is that the outcome of this always has to be a positive number, right? We cannot have a negative number after we take the square root of something. And so to fix that, we put the absolute value bars there. So anyway, the last step again in this case is to take that square root. And so the radius of convergence in this case is just 2. Okay, and that's where this problem ends, right? It only asks for the radius of convergence. All right, so in the second one, similar situation, just, do what we've been doing. That is replace all the n's with n plus 1s. Simplify as much as you can. And you see how Michael's doing all the simplifications there. And then you reach this point at the end where the only things that are left are the x minus 3 in absolute value and the 2 in the denominator. And so that's the thing that you have to set less than 1 at this step right here. And then again, you need to get it to the point where it's x minus a number is less than something. And that something that you get, in this case 2, that is the radius of convergence. Okay. Now in this case, we had to keep going, right? So we had to change this absolute value inequality into a compound inequality, which is what he's doing there. Greater than the negative, less than the positive, add 3 to everything. Then you find your left endpoint is 1, your right endpoint is 5. So this converges on that interval from 1 to 5. Any number between 1 and 5 that you plug in there, you're going to get a series that converges out of it, okay? Now we also have to check for the endpoints, right? Because if you plug in either of those endpoints, you know you're going to get 1 for the ratio test, and you can clearly see that, I think, if you see that if you plug in the number 1 right there, 1 minus 3 is -2, but absolute value makes it positive. 2 over 2 is 1. Can't have 1 for the limit of the ratio test. It's inconclusive. And the same thing happens when you plug in 5, right? 5 minus 3 is 2 over 2 is 1. Again, so either endpoint, ratio test is inconclusive, and so you must use another test. So when x equals 1, what happens? Well, you can see, plug in 1, you get a -2 here, right? Split that -2 to the n as -1 to the n times 2 to the n. And you see when you do that, that cancels with the 2 to the n there, right? That's why that 2 to the n is gone. But the -1 to the n stays, the n to the third stays, and that 1/2 stays. Well, you can see that that series that results here, this, there's no way that's going to converge. Diverges by the divergence test, which basically says if you take the limit as n goes to infinity of n to the third, really technically speaking, that would be like part 2 of the alternating series test, since this really is an alternating series, but it's really the same thing. What is that limit? Well, it's certainly not 0, right? It's infinity. And the divergence test and that part of the alternating series test both say that you have to have 0 there. And if you don't, it diverges. Okay, so certainly that's going to fail the alternating series test. And then this one where you plug in 5, this is not an alternating series, so clearly the divergence test is going to work on that one. So it doesn't converge at either endpoint. And so the interval of convergence, we have to say excluding both endpoints. Okay, now this third problem, the one that I said I wanted to kind of go through a little in more detail, I see what Michael has written here is fine to show sort of the overall, like what's going on with this particular problem. You can see what he's done here. He's actually written it out longhand, right? This is all written out longhand. In other words, starting at n equals 0, if you plug in 0 there, you get -1 to the 0 power. That's just 1. Plug in 0 there, you get 1. Now, this denominator, you have to realize that 0 factorial is actually defined to be 1. In case you didn't know that, that's to avoid the problem of dividing by 0 if you do happen to have a factorial in the denominator. So 0 factorial is not 0, it's 1. And so basically, when you plug in 0, you get 1. When you plug in 1, what happens? Well, this is now a 2n, right? And so you get x squared, you get 2 factorial on the bottom. When you plug in 2, you get this. When you plug in 3, you get this. When you plug in 4, you get this, etc., right? So basically, he's just writing it out longhand and then differentiating each one term by term. So f prime of x, you can do that either with the summation notation. So summation notation, this is just a power function here, right? X to the power of 2n. That's a power function. How do you take the derivative of a power function? You use the power rule. What does the power rule say? It says to take the exponent and put it in front, right? And then, so there it is, and then lower the exponent by 1. You see? So that what he's doing there is simply the power rule. That's it. And then notice what he does. What else he does? He fixes this denominator here and 2n factorial, and then writes that as 2n instead. 2n times 2n minus 1 factorial. Cancels the 2n's there, and then just left with this thing here. And then when you write that out longhand, this is what you get, right? That's all the terms that you get when you write that thing out longhand. And then you take another derivative. Yeah, so you lost the first term to the derivative, right? So this is an important thing to note here, that the first term is now lost. And so it turns out that you can, you have to bump up the index by 1. You see, everybody kind of see why that's happening? The index was 0, but when we took a derivative, it had to change to 1. And why did that have to happen? Because that first term is actually gone now. And if you tried to leave that at 0, then you'd have a problem. If this started at 0, then you would have a -1 factorial. Well, that doesn't even mean anything. You can't have a -1 factorial. So this index has to change. If your first term of your power series is a constant, and you take the derivative of that power series, then you have to bump the index up by 1. Okay? I hope that makes sense, but we'll definitely see more of that. Another point that we're making with this problem is that we have a power series that we started with here, right? There's a power series, and what do we do with the power series? We took its derivative. So what we're seeing here is that you can take a derivative of a power series, right? And if you remember what I told you about power series in the first place, what are they? Kind of another way to view them, they're infinite degree polynomials, right? And so certainly you can take a derivative of a polynomial. In fact, it's the easiest thing to do is to take a derivative of a polynomial. All you got to do is just use the power rule. So very easy to differentiate these things. And then you can also take a second derivative, as we're doing here. So here's the second derivative. Notice that the first term of our derivative, our first derivative, was not a constant, right? There's the first derivative, has a non-constant term as the first one. We took that derivative, and its derivative remained, right? It didn't change to 0. And so in that case, the index doesn't have to change. If you see what's the difference here. The difference, again, is that the first term of our original function had a constant. When you differentiate a constant, it goes away, okay? Now, when we look at the derivative function and try to take its derivative to get the second derivative, we look at this function. That is not constant. When you take its derivative, it doesn't disappear, right? This derivative didn't disappear. And so we don't have to change the index in that case, okay? I know this is kind of a lot to think about, but it's important to understand how this notation is working, this power series notation. Okay, now one other thing, this is great. I don't really have to go through this in any more detail, except for one thing I would note here is that typically we kind of like to stick with the same starting index as the original function. So if, when you take a derivative, it ends up like this, where you do have to raise that index by 1, you can actually fix that and make it go back to being 1. In fact, I'll show you how that works. Suppose I want that thing to start at index 0 instead, so that it kind of matches that first function a little bit better. If you want that index to start at 0 instead of 1, you can easily do that. Remember, I think I mentioned this before. If I'm going to lower that by 1, then I need to raise all the other occurrences of n by 1. So in other words, all those other n's have to be raised by 1, okay? And so what's that going to look like? Well, you're going to get negative 1 to the n plus 1, x to the 2, and then this actually, you're going to remember it has to be n plus 1, and then a minus 1 there. In parentheses, you're only replacing the n with n plus 1. And then in the denominator, same idea, we'll have 2 times n plus 1 minus 1. All that will be factorial. And then if you simplify that, what do you get? You get negative 1 to the n plus 1. Now look what happens there. It's 2n plus 2 minus 1. So that's 2n plus 1. So x to the 2n plus 1. And then this 2n plus 2 minus 1 is, again, 2n plus 1. So you get 2n plus 1 factorial here. Now, if you were to do this with that second derivative, the same thing, in other words, make this second derivative start at index 0 instead. Like, what if I wanted that thing to start at index 0? And I might just recommend, next time you try this problem here, Michael, just make that first derivative go back to 0 before you take the second derivative, because then it's easier to see that the power series that we get for that second derivative is going to almost exactly match the original function. It'll be easier to see it if they have the same index.
Yeah, make it look like the sine and cosine functions now.
Yeah, exactly. Yeah, so, and then the two, same thing, I'll skip the steps here. That n gets replaced with n plus 1, so you get 2n plus 2 minus 1. You get 2n plus 1. Oh no, I'm sorry, I'm doing this on the wrong step here. I'm trying to change that so that its index is what we want it to be. So we'll get x to the, I have to change that to n plus 1. I have to change that to, that's going to be 2n plus 2 minus 2, so I'm just going to get x to the 2n there. And then the denominator, the same thing, I'll just get 2n there, factorial. Now notice that when you have negative 1 to the n plus 1, that is the same as negative 1 to the n. It's, I mean, if you look at the properties of exponents, it's clear. This has to be written as negative 1 to the first power. And so what you can do to rewrite that is just put the negative in front and call that negative 1 to the n, x to the 2n over 2n factorial. Now, if you compare that to the original function, look at how that compares to the original function, the one we started with at the top here. See that? It's the same thing. In fact, it's not quite the same thing, but almost the same, right? What's the only difference? Just that minus sign there, right? And so what is this telling us? It's telling us that when you take the second derivative of this power series, you get the negative of the original power series. Okay? Now remember, these power series are just functions. They're just simply functions. And so when we see a function that when we differentiate it 2 times, we get the original function but negative, that should remind us of another function. What function has that property where you take 2 derivatives and you get the negative of the original function? Well, Michael's already noticed sine and cosine have that property, right? Sine and cosine have the property where you take 2 derivatives, you get back to the original function but negative, right? Second derivative of sine is negative sine. Second derivative of cosine is negative cosine. Okay? So remember what I also said about these things called power series. They are just fancy functions. And if you also remember, I said that any function can, it turns out, be represented, any function that has continuous and infinite derivatives can be represented as a power series, okay? And so what we're actually seeing here is the power series representation of, I don't remember which one this one is. This is cosine or sine?
I don't remember.
I don't either. It's either sine or cosine. I can't quite remember. But what we could do is graph it to see. In fact, this is a good one to practice, to at least see what the graph might look like. So let's take a look at the graph. Let's graph that power series that we were just playing around with. So -1 to the n. I want to put a fraction here. -1 to the n. I don't want to make this go to 1,000 right away. Let's put it just at a small number to start with. -1 to the n, x to the 2n divided by 2n factorial. Yeah, now look at that graph. This should answer the question of whether it's a sine or cosine. What does it look like? Remember which one starts at its amplitude? Cosine does that, right? So what we're looking at here is the graph, the power series representation of the cosine function. Now, in fact, what I could do here is I could put a slider on the top, and then I could say, let's move that slider from first degree polynomial up to, I don't know, let's go to 100th degree polynomial. And we'll step by 1. Okay, so again, thinking about what we're doing here, remember, what we're doing is we're noticing that power series can represent other functions. Well, look at that. When I have a being just 1, then this is a second degree polynomial, which is just a quadratic, right? You see that? Just a regular old quadratic. Now, when I move that slider up and I make it that would make it a 4th degree polynomial, right? Now it looks kind of like a 4th degree polynomial. Bump it up again. Now it's a 6th degree polynomial. Then 8th, 10th, 12th, and so on, right? Well, look what happens as I increase it. What is it doing? It seems like it's actually, as the more terms that I include, the closer that this is actually looking to being the cosine function itself. See what I'm doing there? So I can just keep going and make this look as cosine-y as possible, right? See that? And if I go to, imagine what happens if I take this all the way to infinity, even though the computer wouldn't be able to handle that. But theoretically speaking, if I take this all the way to an infinite degree polynomial, what should those tails eventually do? Eventually, they're just going to keep going forever. And what do we have here? We have the full-on graph of the cosine function. So what this is kind of showing us is that a power series can actually be exactly the same as a familiar function, like a cosine, if I make that go to infinity. All right, so kind of see maybe where we're going with this, and maybe why might we care about doing this? Why don't we just use the cosine function if we want to talk about the cosine? Why would we want to change it into a power series in the first place? Well, it turns out power series are very nice to deal with simply because they are fundamentally just polynomials. And it's much easier to do stuff with polynomials, as in take their derivatives, take their antiderivatives, that kind of thing. And so if you think about it, the sine and cosine functions are actually what's called transcendental functions. They're not even algebraic. They're actually kind of hard for calculators to deal with. So if you have your calculator and you think about the way that your calculator evaluates, for example, you plug your calculator, what is the cosine of 5 pi over 6? And your calculator spits out a number. How does it do that? How does your calculator do that? well, what do you think the calculator is using to evaluate the cosine function? It turns out it's actually using its power series expansion. So if you are maybe, I'm anticipating a question about when would we ever use these things? Well, suppose that you wanted to be a programmer for TI, for Texas Instruments or something like that, and you wanted to help them make these calculators. What are you going to be doing to program this calculator? Every single function that's on here is actually a power series, not the function itself, but its power series representation. That's how the calculator deals with every function, in fact, is their power series, okay? Well, I shouldn't say every function. If it's a polynomial to begin with, then it wouldn't need a power series, but any function that isn't a polynomial or isn't a nice power function like that, it would be doing its power series expansion for it. It would be using it to calculate stuff. All right. So that brings us then to the next section. Like, well, if it's possible to make any function into a power series, or at least any function that has multiple infinite derivatives, if it's possible to do that, how do you do it? What's the procedure to do this? And so what we're going to see in the next section in 11.9 and 11.10 is a couple of different ways to determine power series expansions for various types of functions.